Hello everyone, this is exercise class 5 and I will be going through the two questions in the problem set. So let's begin with the first questions. So in question 1, you asked to do a multiple expansion of the potential along the z-axis given the charge density that I have given you. And so you're not just asked to compute the monopole, dipole, or the chargeable terms. You're also asked to determine all the long Venetian terms. So let's record how the multiple expansions looks like. And so as you can see in equation 3 here, so here is a multiple expansion of the potential, but you should keep in mind that the angle in the Legendre polynomial here, the gamma prime is the angle between the R and R prime. So the gamma prime here is not the polar angles of the differential element. So you should not mistake it for the theta prime. The two angles are completely different. But in the question, I only ask you to compute the potential along the z-axis. And in this case, the polar angles will be just exactly equal to the gamma prime. And then you can simply replace the gamma prime with the theta prime here. So the derivation is very straightforward. So you just need to substitute the charge density that I have provided to you into the expression and also expand the differential volume. So here is a dv prime. Then it's just r prime square sine theta prime, the r prime, the theta prime, and the phi prime. And in equation 7 here, so we grouped all the r prime terms together. So we have the r prime to the power n and the r prime square and another r prime square. So we have n plus 4 and also the exponential term here, the d to the power minus r prime. And then we also group all the theta prime terms together, the Legendre polynomial and also the sine theta prime cubes. Then here we just have two integrals to do. One is over the phi prime and one is over the r prime, and the last one is over the theta prime. So for the first integral, it's very simple. Then the solution is very trivial. It's just 2 pi. And for the second one is the integral. So the integrand here has the r prime to the power n plus 4 and the exponential term. So if you encounter such integral, then you should recognize the solution will be simply the factorial of the power here. So the power is n plus 4 here, and the solution is simply n plus 4 factorial. And then the last integrals is the one which we have the Legendre polynomial. So the question is, how do we evaluate these integrals when the n here can go from 0 to infinity? So I have provided a hint in the questions. So the Legendre polynomials are orthogonal, and if you have two Legendre polynomial, and when you integrate them from -1 to 1, and they will be zeros if the m and n are not the same. So it would take the form like this. It's just 2 over 2n plus 1, and we have a delta function here. Or to be precise, quantitative delta mn. And then what we can do is we take the 1 sine theta prime, and then we replace the d theta prime with d cosine theta prime. So we have the minus sign, and the minus sign will flip the bounds here. So this one is from 0 to pi, and then after absorbing that minus sign, the bounds here will be from pi to 0. And because the sine square theta prime is just 1 minus cosine square theta prime, and then after we substituting the cosine theta prime with x, then we have the expression here. It's the equation 16. And then if we want to make use of the orthogonality relation here, then the next thing that we should do is to try to express the 1 minus x squared here in terms of the Legendre polynomials. So you may just simply look up a table, and here is a Legendre polynomial from the 0th order to the 3rd order. And after some algebra, you should be able to show that the 1 minus x squared can be expressed as 2/3 times p0 minus p2. And then we substitute the expression here into the integrals. So we have our original integrals, and then we do some substitution, and finally we substitute the 1 minus x squared with the Legendre polynomial. And then now we can make use of the orthogonality relations. So here we can simply substitute the solution here, and the integral between Pn and P0 is simply delta n0, and the factor here can be simply obtained by substituting n to be 0. So we have 2 over 1, which is 2, and the second term is a P2. So we have the delta n2, and then we substitute the n with 2, so we have 2 over 5 here. And finally, we put the results together into our original integral. So here is an integral of 5 prime, so it is 2 pi, and r prime here is just a factorial, and the last one, the Legendre polynomial that we have just solved here. And then after some simplifications, then only the 0th order terms and the second of the terms specified, and all other terms will just vanish. So you will just have a very simple expression of the potential in this form. So which is 1 over 4 pi epsilon naught times 1 over r minus 6 over r cubed. But keep in mind that the expansion here is only valid along the z-axis. So although I didn't ask you to do a more general expansion, but you might be curious about what if we want to know the expansion over the whole space in some large distance. So let's recall the charge density. So if you can recognize the charge density here is independent of the phi. So it is a azimuthally symmetric system. So here is the trick. So whenever you have a system which is azimuthally symmetric, then you can obtain the more general solution of the potential from the potential along the z-axis by simply multiplying each 1 over r to the power n plus 1 term by the corresponding Legendre polynomial. So here in the potential along the z-axis, we have the 1 over r and the 6 over r cubed, which correspond to the zeroth order term. So because it's n plus 1, then the corresponding Legendre polynomial will be of order n. So we can obtain the more general solution by simply multiplying the 1 over r by p0 and the 6 over r cubed term by p2. So this one will be the more general solution, not just along the CS, but over the whole space in some large distance. So in the lecture, you are taught the expansions in the form equation 59, and in the beginning of the exercise class, I have reminded you don't mistake the angle that I'm applying here with the theta prime. So it's also possible to express this expansion in terms of the r prime, theta prime, or the phi prime, or the coordinates of those differential elements. But it will involve some more terminated functions, the y and m here. So if you want to express the expansion in terms of the theta prime, phi prime, and r prime, it will take a formula like this. So the y and m here is called spectral harmonics, but this one is not in the syllabus. So it's just for your interest. If you're interested, you might check out more about it. But the form here will be more convenient for you to do the integrals, because here all the variables, the r prime, the prime, and phi prime here can be naturally used to compute the integrals. And then this is the question 2, the second question. So in these questions, you have a hollow tube which has some conducting walls, and among the 6 planes, there are 2 walls that are held at a constant potential V0, and the other 4 sides will be at 0 potential. So the first part of the question is to find the potential at any point inside the tube. After you have solved the potential, the second part would be solving the charge density on the surface, Z equals to A. So the question is simply to solve the Laplace equation, which is subject to these boundary conditions. So the 4 planes here, the x equals to A, 0, x equals to A, and y equals to 0, A, have 0 potential. And for the 2 walls on the Z planes, they are held with some constant potential V0. So because the system is a tube, so it will be most convenient to use Cartesian coordinates. So here we use the method of separation of variable, then we assume the solution would take a very simple form, which is just a product of three functions that only depends on x, y, and z. And then we substitute this trial solution into the Laplace equation. Then we would get equation 42. And then we divide each side by x, y, z. Then we will get equation 43. So because the sum of these three fractions is equal to 0, and because each term here only depends on its variable. So here it only depends on x, here they only depends on y, and this only depends on z. So in order for these three fractions to be summed to be 0, then each of them has to be equal to some constant. And then we can, by inspecting the boundary conditions, so here, because along the x-axis, the wall along the x-axis, the potential are 0 on the two walls that is on the z-axis, and then along the y-axis, the two walls are held as 0 potential, which means the solutions of x and y they have to consist of some sinusoidal functions. So here, the x prime over x here has to be equal to some negative numbers, and the y prime over y here also has to be equal to some negative numbers. So for simplicity or convenience, we can simply let it to be minus k squared and here to be minus l squared. But you are also welcome to not going too fast, and you can just simply assume them to be equal to some constants that could be zeros or positive or negative. But finally, if you want to match the boundary condition, you will see that it has to be negative. And then because we have set the ratio here to be minus k squared and the ratio of the y here to be minus l squared, then the ratios of c prime and z here, in order to satisfy the equation for these three, it has to be k squared plus l squared. So because we have the trial solution to be taking this form, and then so for the four boundary condition here will imply that the x of 0 to be equal to 0, x of a to be equal to 0, and also y of 0 and y of a to be both equal to 0. So we can first solve for the simpler differential equation, the x and y first. So here they are the two differential equations and also their boundary conditions. So you should recognize the solution of this differential equation to be some sinusoidal functions. So here the general solution of x will be a sine kx plus b cosine kx. And the next thing we need to do is to impose the boundary conditions. So first we impose x of 0 to be equal to 0, then we substitute x to be 0, then here we sine 0 is 0, but cosine 0 is 1, which implies that b has to be equal to 0. So we have the terms here, the cosine term here to vanish, and then we impose the second boundary condition, which is the x of a equals to 0, and we substitute x by a. So here, because A can be 0, otherwise we would have X to be 0. So here, which implies that psi Ka will be equal to 0, which means Ka has to be equal to m pi. So m here will be some positive integers. So here we have obtained the so-called eigenfunctions of these differential equations, which is say psi of n pi x over a. So here we can also call the k here to be the eigenvalues. So we have the km to be equal to m pi over a. And similarly, the differential equation for y is just the same for that of x. So the solution is also taking the exact form, except we have the m to be n here to distinguish them, and also we have the y here. So the solutions of y would be psi m pi y over a. So after solving the x and y, and because as you can see, the solution of z is actually related to the solution of x and y, because they are related by the k and l's that are solved from the differential equation of x and y. So for each m and each n, we have the corresponding solutions. So here is the original differential equation of z, and then for each km and for each ln that we have from x and y, then we would have a corresponding solution for z. So we should take the form like this: z prime prime mn equals to k m squared plus n plus l n squared times z mn. So the general solution of this differential equation would be some hyperbolic sine and cosines. So which is simply equation 55 here. And then we can substitute the Km and Ln that we have solved in the previous slides. So the Zmn will be simply taking this form. So the general solution of this potential would be simply some linear combinations of the eigenfunctions. So here we have for each m and n, we have the solution to be this one, the z, the x, m, y, n, and z, m, n. So for each m and n, the solution will be a product of them. But the Laplace equation is linear, so all the combinations or linear combinations will be the most general solution. So which means which we can write the form like this. We expand the x, y, z to be the function that we have solved. And here, for simplicity, I have defined the JMN here to be the JM squared to be KM squared plus LM squared. But it's just a simpling. But it just to avoid the equation to be too long. So here we have two coefficients, the C, Mn, and the Dmn, to be not yet determined. So the last thing that we have to do is to impose the last two boundary conditions to solve for the Cmn and the Dmn. So first, we impose the first boundary conditions, which is at z equals 0, the potential is V naught, So we substitute Z to be 0, then we get the general solution to be uh, collapsed into this form, because when Z is 0, then the hyperbolic sign here is 0 and hyperbolic cosine here is 1. So we just have the DMN here. So therefore we have the summation here to be equal to we know. So in order to determine the DMN, we make use of the orthogonality of the eigenfunctions. We multiply both sides of the equation by the sine n prime pi x over a and sine n prime pi y over a, and then we integrate both sides over x and a from 0 to a. So this is the left hand side and this is the right hand side. So on the left hand side, if you remember, the integrals of the sine m pi x over a here and also the sine m prime pi x over a here, the orthogonality property implies the integrals of these two terms here would be just a over 2 delta m prime. And also the y term here, the integral will also give a over 2 delta n prime. So because we have the delta function here, so only the terms in this infinite series equals to m prime and n prime will spread. So finally we have a square over 4 and d m prime n prime, because we replace m by m prime and n by n prime. So on the right hand side, it is just a very simple integral. So we have two sine function here. So we just do the integral and you should be able to get equation 68. And then after solving both integrals, then we put everything together. Then we rearrange the terms. Then we will be able to see that the DMN, the coefficient, will be equal to this one. And then we impose the last boundary conditions. So similarly, we just substitute z to be a, and then we multiply both sides of the equation by the sign here, and then we integrate them over x and a. So because the procedure is very similar, so I do not give the very detailed derivation, but you should be able to get the left hand side to be equal to something like this. The right hand side, because it is just the same integral, so it is still the right hand side that we have computed in the previous slides. And after we arrange the terms, then you should be able to show that the CMN will be equal to something like this. And then we substitute back the DMN that we have solved, and also make the expression more organized. Then you should be able to get the expression 77 here. So I think I have missed a bracket here. And then the next thing is to put all the coefficients, the CMN and the DMN, into the general solution and make it more organized. And then you should be able to get equation 79 here. And then if you are careful enough, you should recognize that the m and n has to be odd, because when m and n are even, which means the term here will be 1, then 1 minus 1 is 0. So only the odd terms here will suffice, so we can further polish the expression. Then instead of having the m and n going from 1 to infinity, then we can just specify the m and n has to be odd, and when the m and n are odd, then here will be 1 minus 1, then this one is 2, and this one is also 2, so we have 4 here, then that's why we have 4 times 4, so this one is 16. And so if you want, you can also do a further simplifications by making the terms here, the z terms here, to be locked a bit simpler. So I did not show you how to simplify it, but it is quite straightforward. So we will so you should be able to simplify the terms here, the two hyperbolic sine function here, the hyperbolic function here, to be something like this, which is just one hyperbolic cosine over by another hyperbolic cosine. So this is the answer of question 2a. So then for 2b, so you're asked to find the surface charge density on the surface z equals a. So in order to find the surface charge density, you just need to simply use the boundary conditions. So because that is a conductor, so you can only get the charge density that is in the surface that inside the top, in the surface that inside the tube. So for the term here, it will be just 0. So it's a conductor. So the electric field outside will be just 0. So you just have the field that a non-zero field that below the surface. So here we have the minus epsilon naught E Z equals to the surface charge density. So because the electric field normal to the surface is simply the minus rho v rho z. So the charge density is simply epsilon naught times the derivative of the potential with respect to z. And after doing the differentiations, then you substitute the z to be a. So this one is just the derivative of the solution that we have gotten. Then after getting it, you substitute the z to be a, then you should be able to get the charge density to be in this form. So this is the end of the exercise class. So if you find anything confusing, or if you find me skipping some really essential details, then just send me an email and ask me to clarify it a bit. So thank you.